Okay, let's resume. We have been, a quick recap of what we were up to from a different standpoint is the fact that we were trying to realize amplifiers based on certain requirements and specifications. So when you put yourself in the shoes of a designer, what essentially are you doing? You are essentially starting off with some sort of requirement, right? So this is essentially the flow chart that all designers follow to some extent, right? So you first start off with some requirements. And these requirements need not be homogeneous. By that, what I essentially mean that the requirements can come in any sort of specifications. It might not be that I want an amplifier with so much gain, so much this, so much that. It can be that I want a VCVS, or it can be I want an amplifier with so much gain. It can be that I want steady state error to be so much, and so on and so forth, right? Or it can be I want the step settling to be within so many nanoseconds, right? So these requirements can come in any shape or size. So, but you start your design from a requirement, and once you know what the requirements are, what do? You essentially generate a block diagram. So you generate a block diagram, assuming that you have everything ideal. Okay, so you list out the components, your dream components that you require to realize these your requirement. You strip it down and you generate a block diagram. And once you have a block diagram, you try to replace the elements of a block diagram with an incremental model. When I say incremental model, what I essentially mean is that obviously this is a circuit design course. This is not a generic design philosophy. So now if you have to realize the block diagram, you are realizing the block diagram using certain control sources. And since this is in our case, the only control source that we have at our disposal is a voltage control current source, also a transistor. So essentially, you have to replace the block diagram with an ideal VCCS plus other passives. Right? So you realize, you try to realize your block diagram using this. And once then you analyze and see whether your block diagram, whatever you started off with, meets the requirement or not. You analyze at every step, but overall you'll have to you will have to satisfy yourself that whatever requirements you started off with in step 0, you are on course, right? So if you satisfy that, then you can, then the last step is replace your VCCS with MOSFETs, right? So replace VCCS with MOS transistors. And even though this comes within the domain of this step, but I am putting in another extra step, that is just replacing the VCCS with MOS will not suffice. You'll have to give biasing to the circuit. So you'll have to give bias, apply bias, and also you'll have to make room for applying incremental input, right? So we are all looking to design something which is supposed to take in some time changing input or incremental input. So you have to apply this appropriately, and then you go ahead and analyze whether your stuff is ready to be shipped, right? So this design flow, right? This design flow from top to bottom, we call it a synthesis. You are synthesizing something from nothing. You started off with something. You started off with nothing, with a requirement, and you ended up with a circuit. You designed something from 0. Now, since this is a synthesis, you will often find that there is no single solution. You might have multiple solutions, and that is okay. But only leaving it here will not suffice. You'll have to, once you come to the final step, you'll have to go back and see whether the initial requirements are met or not. And not only that, whether you have in the process of synthesizing, whether you have knowingly or unknowingly hampered the overall functionality of the system, right? So that part, that when you do that, you go this direction, and that is analysis. So in principle, as long as you know maths and you know KCL, KVL, analysis should be simple, right? Because going from bottom to top, there is only one solution, right? Given a circuit, there can be only one output. But given a requirement, there can be multiple circuits. So that is why this loop is important, that you have to first synthesize and then go back and check whether you are analyzing it. Whether you use your analysis skills to figure out whether the requirements are met or not. So if you go back to all the lectures, you will see that this is what essentially we are trying to do, right? We started off with a requirement. We are trying to, in some heuristic way, we came up with some architectures, and we are still in the process of realizing an amplifier based on requirements. And once we reach every step, we do an analysis back test essentially to see whether the requirements we are still on track or not. If not, we go and change something. If we are on track, we proceed to the next step. So this is what we have been doing, right? So this is another way of looking at any design with the domain of circuit design in the perspective. Okay, so when we just before the midsem, we were looking into biasing our transistor with currents while applying a current source. And the reasons were the fact that one of the reasons that we saw was if we bias a transistor using current sources, then the small signal or the incremental parameters are much more immune to changes with respect to ambient conditions, right? So then we saw that there are multiple ways of applying current sources and multiple ways of stabilizing your transistor based on negative feedback, right? So we saw there are ways of we apply ID, or rather I naught at drain. Then you sense the voltage at the drain, and you feedback the information at gate. You can apply I naught at drain. You can feedback the information at source. You can do the same thing at source, feedback at gate. Right, so these are essentially the four possible combinations that we argued that are possible, and among these we ticked off this one and we ticked off this one, right? And let's move ahead and look at a couple more of them. Okay, so let me take this into account. So that is, we will apply the current source at the drain, and we'll sense whatever is happening at the drain voltage and try to tweak the source terminals. Okay, so obviously you need to have a current source, and we already said that we'll be tweaking the source, which means that my gate has to be some constant bias. So we'll have to apply something at the source, right? So before we get into applying anything at the source, what do? We argue with ourselves that what is the drain voltage, and from there, how do I get a sense of whether in which direction I need to move, right? The sense of feedback should be right in order to figure out whether negative feedback is working or not. So now let's argue. So you will have drain current ID. So if now you imagine yourself, you are sitting in the lab, you have control of the source terminal, and you are observing V naught, and you observe that V naught is increasing. Then what is the conclusion? ID is less, which means you have to increase ID, right? ID is the control source. You can change ID. You have to increase ID. And how do you increase ID? Given that you don't have any control over gate, you have fixed the gate voltage. you have to increase VGS, and if gate is constant, which means you have to reduce the source voltage, right? So you'll have to essentially you'll have to invert V naught and then apply something at the source. Okay. So now, I mean, now you know the drill, right? We have voltage control current source. So if V naught is increasing, I need to decrease this. Okay. So how do I decrease? How do I decrease any voltage? I pull current out from that node, right? So essentially, if I just say that I have a control source, and the direction is as I have shown here, I will connect it here and get rid of this stuff. Then it is possible to then obviously I haven't shown the controlling terminals here, but the argument will be we have to connect up this control source in such a way that as this voltage increases, this voltage decreases. And I know that if I have a voltage control current source, right, which is essentially a MOSFET, and that if I observe the drain of the MOSFET that and I increase the gate voltage, this is exactly what we end up with, right? So what is the obvious conclusion here? The obvious conclusion is that I observe this voltage is VG or not V naught, and drive a current GM2 times V naught out of this node. And obviously, if I connect it in this fashion, you can figure out that if V naught increases, I am pulling current out. I am pulling current out of this node. And now if I connect this node, let's say V02, if I connect this node V02 to Vs, then in this, at least the sense of the negative feedback is maintained. Right? Do you agree? You don't have to get into whether this will work or not at this stage. You'll have to just get into the fact that whether the argument that we started off with, if V naught increases, Vs is decreasing, that argument holds good or not in this configuration. Do you think it holds good? It holds good, right? But would it have been fine if I had connected, let's say, if I had connected these two nodes? Clearly not, right? There are multiple problems with this. First, the sense of the feedback is not right, because if you argue, if V naught, you break the loop anywhere. Let's say, assume I break the loop at V naught. I break the loop here. I increase this voltage. Then what is happening? You are pushing current into Vs, which means this is increasing, which means this further will increase. So this is positive feedback, right? So this clearly will not work. And also, yeah, you should be able to understand that what is the effect of these things. These are essentially acting as error amplifiers, right? And which means you need high gain. Error amplifiers, you need high gain. And if you look at this is a source terminal. If you look at the output of the source terminal, then you will get low impedance, you will not high gain, and so on and so forth, right? So obviously, even if the feedback, even if the sense of the feedback were right, you wouldn't be able to connect the source directly to this source because you wouldn't have gotten any gain. But that is irrelevant here because the sense of the feedback itself is incorrect. So the only option is connect this to this. Okay. Any questions? Are you satisfied with the argument, or you want me to explain it in some other fashion? Okay, if you are satisfied, let's go ahead. So now, if I go back to this flow chart, where are we? We are essentially here at this step. Okay. Not even that step. We are at this step, right? You have used ideal VCCS, and now we'll have to get into this step. I'm sorry, Sorry for the flip-flop. So now we'll have to get into this step where we replace the VCCS with MOS transistors, right? So now, so what should we do? So what I'll do, I'll redraw this because this might seem messy a bit. So what I'll do is, I mean, what we are essentially seeing here is the drain. This is the drain terminal, right? The drain terminal of the second MOS transistor, whatever would have been the MOS transistor, has been connected to the source of the first transistor, right? So now first replace. Let's keep this incremental model as is. This is grounded. This was the drain of, let me call it D2, right? This is D2. So this is D2. And we were observing this output. And this was V0. And this was supposed to be GM2 times V0. Okay. So this essentially is, basically I redo the same thing. Now it's easier to replace. You can visualize it easily. What will happen if I replace this GM2 with a MOSFET, right? So let's do this. Okay. So this, once you replace the GM2 with a MOSFET, this is the configuration that you end up with. But note that I haven't yet applied any bias. I mean, even though I have showed a bias here, I mean, I haven't yet established what that bias needs to be. We are not even sure whether this M2 is biased properly, or we'll have to do something to get it to to be biased properly. So then we'll have to go back and analyze. Right? This step, I mean, you ended up with you synthesize something. Now you'll have to go back and analyze whether this will work. If it works, under what condition it will work? Is there a range for which it will work? And so on and so forth, right? So let's see first whether it will work or not, right? So what is the first thing that you will need to figure out with in your mind? What is the next step that you will ask yourself to figure out whether this will work or not? From when I say it will work or not, what I mean is that whether at least it will be biased properly or not, right? Or whether we'll have to apply a bias, which means what are we arguing with ourselves? We are arguing that whether the transistor will be in saturation, at least, right? So everything we have been doing is assuming that this when we are saying that my VCCS is of this model, we are inherently assuming that the transistor has to be in saturation. Otherwise, this model is not valid. Okay, so which means that I have to first establish whether if I connect up my circuit like this, connect up a couple of transistors like this, whether this is still in saturation or not. So if I have to figure out whether this is in saturation, what is the most important thing that I have to look for? Pardon? VDS and VGS, right? So now you have two transistors. You can start attacking, you can choose which one you want to attack. So let's choose M1. Okay. So let's see whether this is VB, whether my transistor M1 is in saturation or not, right? So if, or rather for what ranges of VB is it possible to keep my transistor in saturation? So now let's assume that we have applied a voltage at the gate of M1. If I have to figure out whether M1 is in saturation or not, what is the next thing that I should look for? Okay, so this is one important thing. Is source voltage important while trying to figure out whether it is in saturation or not? It's not, right? Because why? Because ultimately, what is the condition? VDS is greater than VGS minus VT. So source doesn't come into picture. So all you have to take care is whether this condition is satisfied or not. You can forget about the source. And obviously the transistor has to be on, otherwise, I mean, none of these things will be valid. So all you have to figure out is what is the relationship between this terminal and this terminal, right? So assuming the circuit is working, right? Because I mean, what am I after? I am after the condition under which the circuit will work. So assuming the circuit is working, what is the voltage V0 in terms of the parameters that you know? V0 must be greater than, V0 must be greater than threshold voltage of M2, right? Definitely V0 has to be greater, but is there a better approximation? Yeah, exactly, right? So now see, I mean, we argued that this circuit will work because it is supposed to be negative feedback, right? So essentially, this current I0 is fixed, but what is the variable source that is making sure that whatever you are pulling out of V0 is exactly equal to I0? Is it M1 or M2? It is M2, right? So which means that the current in the lower part of the circuit is being set by M2. Okay, so naturally it makes sense to argue that this VGS is the most important parameter as far as ensuring that the circuit is going to be biased properly. Okay, so now since source is grounded, what is your V0? Your V0 will be threshold voltage of this plus under root 2 I0 by mu Cox W over L, right? Okay, and this W over L is of M2, right? So now we have two transistors. So there is one more thing about thumb rule that we follow, most designers follow in design, is when you are starting off, you don't know many things, right? You don't know many parameters. You don't know what is the starting assumption that you should take. Like similarly, when you do any numerical analysis or numerical solver, Newton-Raphson, and so on, you start off with some initial points, initial values, right? So similarly here, if you don't know anything in a design, you say that, okay, I will start off with M1 and M2 to be equally sized, right? So if it's required, later on, if I figure that that is not good enough, I will change it. But you can start off with equal size. So let's assume that they're of equal size. Yes. It need not be diode connected, right? No. Is it required to be diode connected? What is the current through M2? If things are working properly, what is the current through M2? I0, right? Then in terms of VGS of M2, what is the equation of I0? Do you agree? So you basically flip it out, express it in this form. Diode connected is a special case, right? So this is the case as long as M2 is in saturation. We have to ensure that M2 is in saturation. We are starting off with the assumption that M2 is in saturation, but we have to go ahead and ensure that. Are you satisfied or not? Okay. So now if you know that your V0 is supposed to be this, so what is the upper limit of VB? What is the upper limit of VB to still ensure that M1 is in saturation? I'm looking for VB max. V0 minus VTH1. Again, simplified assumption, assume VTH to be identical. Both cases, right? So your VB max will be V0 minus VTH, which is approximately, which is not approximately, in this case, exactly equal to this term, which is essentially the overdrive, right? This is the overdrive voltage of M2. Yeah, assuming VTH is same. I mean, simplified assumption, assuming VTH. So if I write it down, what should happen? Your V0 should be greater than VB minus VTH, right? Right. So you're right. So your VB should be less than equal to V0 plus VTH, which is 2 VTH plus overdrive. Thank you. So this is your VB max. Right? Okay, so now what about the lower limit of VB? So what will happen if so we established that if VB increases, M1 will go towards triode, right? So we don't want that, so that sets the upper limit of VB. What about the lower limit of VB? Is there a lower limit? Or if there is, obviously there will be a lower limit. If there is a lower limit, what part of the circuit will get affected if I breach that lower limit? Is it? Will M1 be turning off? So so essentially what I'm trying to get at here is that if I reduce, let's say VB by delta V, right? If I reduce VB by delta V, what part of the circuit is getting affected? So let's say let's take some numbers, right? So if you take any modern processes, your threshold voltage is approximately 300, 400 millivolts. So this is 800 millivolt. And if you assume, let's say, overdrive of 100 millivolt, so this, or maybe 200 millivolt, it rounds up perfectly. So this VB max is 1 volt, right? So your VB max is 1 volt. Even though you don't bias it at the edge of operation, but let's assume that this is at 1 volt. Okay. So now I reduce from 1 volt to, let's say, 900 millivolt. Assuming things are operating properly, what is likely to happen in this circuit? VS as in what is VS?
VS of M1 in order to maintain the current.
Okay, so let me ask, okay, yeah. So let me ask somebody else from that side of the class. What do you think is going to happen if I reduce the VB by 100 millivolt? So what is not likely to change? Firstly, if you can establish what is not likely to change, it's easy to figure out what else is remaining that can change, right? What is not likely to change? I naught, right? I naught is a constant source, constant, it's not likely to change. So I naught is flowing through M1 and M2. I naught is not likely to change, which means what is not likely to change in M1? VGS. VGS will not change. Now, VGS is not changing, but gate is reducing by 100 millivolt. Then what should change? Source should go down by 100 millivolts, right? So this should go down by 100 millivolts. This shouldn't surprise you. Why this shouldn't surprise you is because if you get into the incremental model, right? If you get into incremental model, what is the gain between this gate and this source? This is a source follower, right? if you assume M2 to be ideal, like no GDS, so which means essentially what is happening if you concentrate on this part of the circuit, right? So what will be the gain between the gate and the source in this case? I mean, it will be 1, right? This is the classic case of a source follower. So which essentially means that when gate moves, the source has to move. And this is again the same thing that happens if you bias with constant current, right?
So gain is 1 or less than 1?
Ideally, we have still not put any non-ideal elements here, right? Okay, fine. So as long as you are satisfied with this, so now we are in a position to figure out what can get affected at the lower limit of VB, right? So now I am reducing VB to figure out what is the lower limit. So what is likely to get affected? M2 will start getting into linear, right? So which means that I'll have to figure out what is the condition under which M2 gets into linear. From there, I can back calculate what is the lower limit of VB, right? So I know already what V0 is. Will this V0 change when I am changing VB? No, right? Because again, same constant current biasing. Current is constant, VGS has to be same, so V0 will not change. So I know that if V0 is not changing, what is the minimum VS for M2 to still stay in saturation? So VS min will be equal to V0 minus threshold voltage, right? So what is V0 minus threshold voltage? This is essentially the overdrive of M2, right? So this is this part. So this is the overdrive of M2. So this is the overdrive of M2. Okay. So I know what is the VS min. I have established what is minimum VS. Now I am in a position to figure out what is the minimum VB, right? So what will be the minimum VB? VS is equal to VB minus, or in terms of VGS of M1, what is VGS of M1 in terms of current and everything? VTH plus overdrive, right? VTH plus under root 2 I naught by blah blah, right? So VTH plus overdrive. So your VG, your VS is essentially gate voltage minus, that is gate voltage is VB in this case, VB minus the VGS of M1, correct? So VS is nothing but the gate voltage minus the VGS for a current of I naught, right? For a current of I naught. So this is what, now help me out. What is this VGS of M1 for a current of I naught? Threshold voltage plus overdrive of M1. Okay. So this has to be, I mean, if you, now that you have established what is VS min, that is V overdrive of M2, right? So this was V overdrive of M2. So what will be VB min? Threshold voltage plus V overdrive of M1 plus V overdrive of M2. Okay, so now if I again put back the numbers, we assume threshold voltage to be 0.4. We assume overdrives to be approximately 200. So this is 0.2, 0.2. So this becomes 0.8 volts. So the maximum limit was 1 volt and the minimum limit is 0.8 volt. I mean, that obviously will change if all these overdrive and threshold voltage and all these things keep on changing. Okay. Any questions?
So if VB goes further below than VB2, in that case M2 will lead the saturation, right?
Correct.
And in that case, the output will not be. I mean, the output will also.
Then you have to go and analyze what. Obviously, I mean, till now we have totally neglected any output conductances and all, right? So your output conductance will get affected. So worst case, what will happen? I mean, let's assume I push VB to I push VB so low that M2 goes into triode, deep triode, right? VDS close to 0 of M2. So then what is likely to happen? Is the question clear? So I established VB to be equal to VB minimum equal to 800 millivolt, right? But I don't honor that. I keep on driving VB to, let's say, 500, 600 millivolt, 400 millivolt, right? So if I drive VB to, let's say, 500, 600 millivolt, VS is naturally going closer and closer to ground, right? If VS is going closer and closer to ground, M2 is essentially going into triode, deep triode, right? VDS of M2 is going closer to 0. So then what is likely to happen? What is this circuit getting transformed into? No, circuit is not getting transformed into resistor. M2 is getting transformed into resistor, right? And if you keep on playing this game, you can say that the resistance of that M2 is almost close to 0 also, right? If you are going close to IDVT equal to 0 around that deep linear thing, your M2 itself, I mean, VDS across M2 is close to 0, that resistance is also close to 0, right? If you go back to your initial assignments of GDS versus VDS and so on, you'll see that it's this, the resistance of M2 is going to 0. Now, resistance of M2 going to 0, which means this feedback doesn't exist, right? So even when M2 gets into linear, your feedback kind of doesn't exist, right? Because this feedback exists only when M2 is in saturation. So if feedback doesn't exist, you can simplify the circuit and say that I can assume VS to be grounded, which means I have a current, I have a control current source on the bottom and I have independent current source on the top, but they are not talking to each other. So your circuit will not get biased. Okay. Okay, fine. So now, any questions? So the reason I'm going through all of these in detail is this is not that this is the most important circuit of the course or this is the most important circuit that you'll ever face in your life. It's basically the fact that I want you to walk yourself through a process of figuring out what the limits are and so on and so forth, right? And if the limits are not acceptable, what are the design tools that you have to figure out it's still acceptable? Okay. So we established that the maximum voltage is maximum voltage of VB is 1 volt, minimum is 800 millivolt. Well, let's say that I'm not satisfied with that 800 millivolt minimum, right? For whatever reason, maybe there is a previous stage and whatever the conditions might be, I'm not satisfied. I want to make it 100 millivolt. Sorry, I want to make it 700 millivolt. That is, I want to drop the minimum VB min by another 100 millivolt. This is often a design requirements, right? I mean, by design requirement, I don't mean that your customer will tell you. It's like while figuring out what to do with your circuit, you will end up in some situations where intermediately you are not satisfied with the biasing condition. You have to change the biasing, right? So I want to figure out what should I do to reduce the minimum VB by another 100 millivolts. So then what should I do? Off? Yeah, I mean, but is it necessary to, we started off with same W by L for M1 and M2, but now it's time to ask the question that is it necessary to have same W by L in both? Or am I losing something? Am I gaining something? Right? So now you'll have to look into the circuit and tell me what will happen. I mean, let's change W by L of 1 at a time, right? So let's change the W by L of M2, right? So, okay, even before changing W by L of M2, why should we change W by L of M2? because yeah, so your VOV, right, the overdrive voltage will reduce, right? So if you are not comfortable in the overdrive voltage model, you can look into this equation and see that if you increase W by L for the same current, that extra term, right, which is the overdrive voltage, will reduce. And you see that here what is happening, your minimum is essentially determined by overdrive voltages of 2 transistors, right? And as she pointed out, if I simply reduce the overdrive voltage of both the transistors, I stand to gain the lower limit of VB, right? So if you have to just simply decrease decrease your VB min by another 100 millivolt, I can say, okay, maybe I'll just decrease the VB min of M2, right? Or I can decrease the VB min of M1, right? So you have 2 handles. And as I said initially, there might not be one single solution to whatever you want to achieve. It looks like here I can do either, or I can do a bit of both, 50 millivolt here and 50 millivolt there. Okay. Okay, fine. So any questions before I move on and apply signal? This is only we have applied bias. Okay, then let's apply signal. So at the end of the day, we were trying to realize this, right? So you want to trying to realize something like this incrementally. Right? So I have a source, I have a source Vi. Where should I add the source? And how should I add the source? We started off, I mean, we can apply in multiple places, but we started off assuming that this is the main transistor where I am trying to apply an input, right? So let's try and apply the input at the gate of this transistor, and you can simply do this. And by the way, when I am doing this, at the back of your mind, you should think what should go on the back of your mind is that you cannot physically connect these two. You'll have to have this resistor divider or some sort of biasing, and then AC couple your input so that the DC and the AC don't get mixed up. So in case you don't recall, this is what I mean. Right? So this is equivalent to adding those two in series at non-zero frequencies for input. Okay, but I mean, we are still planning to take the output from here, right? So maybe we have RL connected here, but will this work if we simply do this? It will work. Why? Why do you say? Okay. But will okay, so okay, first let's see what the Vs, right? So the input, if the input swings here, assuming that you have honored this C1, C2, the C1 is kind of shorted at the signal frequencies, then you'll have Vs here, no issues. But now, what do you want? You want this action. You want this action of GMVS, right? GMVS or GMVI. But will this action take place? Yeah, right. Vs of M1 is not grounded, right? Precisely because this was it was biased with constant current source, right? The current in the stack cannot change. Biased with constant current source means what? You cannot have any incremental current, no non-zero current, and no small signal current, right? So now the good thing about this is that we are not particularly bothered. Your input is not at DC. Input is at non-zero frequencies, which means I can play around with something. Like just like we played around with the capacitors at the input side, can we do something to ensure that I should not use Vs when it's a bad, since we have source, so this is Vi. So what should we do to ensure that I get GM times Vi current incrementally at the output? I should incrementally ground the source of M1. And we have weapon to do that. I can connect CS. Okay. So assuming things are, again, if CS is sized properly, assuming CS is sized properly, at the signal frequency, this will be grounded. This will not swing, right? And at zero frequencies, at zero frequencies where there is no signal, CS is open and you have negative feedback that is holding the bias together, right? So at zero frequencies, what is the CS essentially doing? As I am saying, at zero frequency, this doesn't exist. I have negative feedback, constant current source, things are biased tightly. At signal frequencies, this CS is shorting the source of M1. No negative feedback exists anymore because I am disconnecting the hold of M2, right? There is no, M2 is out of the picture. So since M2 is out of the picture, this M1 acts like a open loop common source amplifier almost, right? So I am getting that extra incremental current, and that incremental current can now flow into RL, right? That incremental current can now flow into RL to realize your gain. Yes.
So when CS was not, suppose CS is not there.
Right.
In that case, if I apply Vi, in that case, Vs is also changing the same way like Vi. That's why there is no.
Right. Correct. Exactly. Right. So it's the same logic, right? So when we were biasing it properly, when we are looking at the bias picture, what we were essentially saying, if this decreases by, let's say, 100 millivolt, this one was also decreasing by 100 millivolt. And why was that happening? It's because CS is open. But if I hold, let's say when I'm applying a signal, imagine this condition. When I'm applying a signal, I am holding this node constant with a battery. And what is that voltage? I am holding that to. I'm holding it to a magic voltage which is set to VB minus VGS of M1. Assume that you have got a battery and you have stuck it in there. So now don't assume that you have negative feedback and all. So let's say you have stuck it in, you have got a battery and you have magically figured out this is the source voltage that I require to sink current I0 into M1, right? So what I'm essentially saying is that with your magical powers, you have got this. This is connected to VB, and this is connected to a battery of VB minus VGS of M1 for a current of I0. How you have got this is a different matter, but you have got this. then this is all you want. Common source amplifier, right? GMRL to be the gain. But the issue is that how do I get this battery? I don't have magical powers, right? So what I am asking is, I am asking the circuit to set up that voltage in itself using negative feedback. And when I'm asking the circuit to set up the negative voltage in itself, it is doing it properly, and I am putting a capacitor to capture that voltage. If the capacitor is large enough, it will capture and stay put. It will not change. It will not let the voltage change. Okay. So that's what essentially the role of a capacitor is in this case. And we commonly say that at higher frequencies or at signal frequencies, the capacitor is a short. Essentially, the capacitor is acting as a battery of the requisite voltage to sink in current of I0. Okay. Any questions?
Sir, these are all alternative solution, or
These are all?
any advantage over the other technologies?
I didn't understand. Can you?
Because when you using these two transistor
Right.
for this,
Right.
so simply we can use or MOSFET and current flow.
You mean, are you trying to get at? We have these 4 ways of biasing. Is there a winner?
Yes.
Right. So the answer to that is it depends, right? So when you are starting off, you don't really. Okay, so that's a very interesting question actually, and very relevant question. What he is essentially asking is that why do I bother? I know how to bias a common source amplifier. I know one way to bias it, and let's use it everywhere. But as it turns out, you will end up in situations where such a biasing, one of the biasing might not be, will not suffice, let's say, right? For example, let's say you are faced with a situation where there are 2 stages. A preceding stage is driving the, succeeding stage, and the preceding stage is also setting up some biases, which means that, so let's assume you have 2 blocks. Right, and these 2 are connected. So when you didn't connect this, let's assume it had a bias range of Vmax and Vmin. Okay, and you only have only one way of biasing, the following stage, right? And in that way of biasing, for example, in that case of, let's assume the case of diode connected, observe at drain and feedback at gate condition, right? So in that case, if you observe at drain and feedback at gate, what, I don't have it here, but if I quickly draw it, so essentially what are you doing? You are essentially saying that this is what I am getting into, right? So now the issue is this has a different Vin and Vmax, right? And if these 2 don't match, then you will end up in a problem. Now you can always say that, hey, I can AC couple. I'll put a coupling capacitor here, and then this becomes my. So I don't have to bother. I can still live with it. But the issue is that you can, when you are doing on-chip design, this value of these capacitors can end up becoming really large, right? So in that case, you will probably not be able to use AC coupling capacitors everywhere. Maybe when you are trying to couple signal from outside the chip to inside the chip, where you can have specific ceramic capacitors sitting outside the chip on the board, like you have a big PCB, then it's fine. But you cannot really use half of your chip just to put a coupling capacitor, right? So which means that if everything is inside and you are not at particularly high frequency, everything is inside the chip, what you will have to ensure is that you design in such a way that the bias condition of the preceding stage, output condition of the preceding stage, and the input condition, required input condition of the succeeding stage match, right? So then all these topologies come into picture, right? So you'll have to then see what are if one doesn't work, do I have something else to play with? Okay. There is one important there is one important difference for this particular architecture also. I mean, one might say that this seems to be a source follower kind of architecture, right? I mean, the other thing that we did before the midsem was we just stuck in a current source at the source of M1 and said that observe at source, feedback at source, circuit gets self-biased. This looks to be similar to that, but there is also an important caveat. I mean, I will not do it here, but what I want you to do is figure out what is the constant on CS, right? Or in other words, what is the time constant associated with CS, right? With this case and with the case in which you had current source at M1, at the source of M1, right? So you see there is a significant difference. And that difference is such that, I mean, the value of CS will come down. Okay, so there are, I mean, so this is where the analysis part comes in, right? So we didn't start off trying to reduce the value of CS, right? So we started off with some requirement, you came up with something, and then see what are the good and bad things about this circuit. If something is not right, you go ahead and change it, right? So that's all.
Sir, is this circuit very much resilient to supply voltage change compared to?
We haven't really gotten into supply voltage change now. I mean, if you have a constant current source, right, and if you assume this current source is constant across everything, then it doesn't matter, right? Whatever you do across the supply, it doesn't.
Because in the previous analysis, you showed that the base voltage, the dB changes in certain rate,
Right.
then the V out does not change.
Right.
The Q point remains.
Correct.
So in that sense, I'm saying that if the supply voltage changes.
So anything that is in negative feedback has some resilience. That's why you put in negative feedback, right? So there was, I mean, in the last assignment, I think I had asked you to see what is the output resistance with and without negative feedback, right? So I'm sure you must have seen that when you didn't have negative feedback, the output resistance was very high, right? It was only capacitive, right? So which means that at low frequencies is infinite. But when you had negative feedback, it was quite low. It was of the order of 1 over GM or over GM times R times GM and something like that. So that is not by fluke. That is by design. Why? If again, you can argue it philosophically. What is the role of negative feedback? The role of negative feedback is to ensure that whatever change is there in the ambient condition should not affect the functioning of the circuit. Okay, so when I say that it should not affect the functioning of the circuit, what I essentially mean is that it should not affect the biasing condition of the circuit. Now, what is a resistance? A resistance is, how do you figure out a resistance? There are two ways. One is you apply a voltage and figure out the current. Other is you apply a current and figure out the voltage. Now, when I say something is high resistance, what I'm essentially saying is that if you inject a current, you will have a lot of voltage change. But what is the negative feedback doing? Negative feedback is preventing that, because you are, by design, you are trying to ensure that nothing changes, right? You would only want the change between input and output, but nowhere else in the loop should get affected, right? So, I mean, this is, if I go back to the, again, classic definition. So between V0 and Vi, you have some desired relation. But if you apply a disturbance somewhere else in the loop, then V0 doesn't respond, at least under DC condition, right? Or responds minimally. So why? This is by design. I don't want any other disturbance to affect the output. So when we say that you have negative feedback and you are trying to figure out a resistance at some node, what are we essentially saying? And you figure out that the resistance is very high. Then what are you essentially saying? You are saying that if there is some injection into that node, some small current injection into that node, the voltage will swing wildly. That's what high resistance means. But when you are designing something in negative feedback, you are exactly trying to prevent that. So when you are putting your circuit in negative feedback, there should not be any high impedance node. Okay, so if you have put your circuit in negative feedback while design phase and you still find there is a high impedance node, which means something is wrong. Your design is not right. Because you are trying to hold the quiescent points steady, right? Which means that by definition of negative feedback, your resistances should go down. Okay. Okay, any other questions? Okay, so let's do one other example quickly. And I'll not do it fully. I'll leave it to you. Maybe I'll put in another assignment. So the last thing that we have kind of delved into 3 other topologies. Let's quickly get into the last, that is you are observing at source and feeding back at gate.
Is there a specific name of this class topology?
Which topology?
This one. Now this.
Well, I mean, not in this context, but in the context of current mirrors, there are some names. We'll get to that. So we were trying to look into we want to get into that configuration where we want to observe the source and feedback the information at the gate, right? So when I say observe the source, which means the constant current source is applied at the source, and I want to feedback at the gate, right? So the gate is not constant biased anymore, right? So now let's argue. What is the argument? If this current ID, let's say I am observing the voltage at source. If source is high, what am I interpreting? The source voltage is increasing. What am I interpreting? ID is high, right? ID is high means your VGS is higher than what I expect, right? So I have to get a corrective action at the gate, which means I have to pull the gate down, right? So now you should be master at this. So you observe this node voltage and you pull current out. I mean, this is not particularly necessary in the incremental sense. So this becomes GM2 times Vs. Okay, and you can have your RL here. And if I simply replace this GM2 times Vs, I mean, this is the ideal voltage control current source model. If I replace this with a transistor, I end up with this. So now obviously I cannot connect this to VDD because then there is no negative feedback, right? Because the gate of M1 then stays put at VDD, but I want gain between these 2 points, which means I can replace this with some R2 and I can have RL here. Okay. So this is another way of biasing my another way of setting up your negative feedback. Now again, I mean, we'll have to argue whether is there a range, is there a maximum, minimum, or rather, how do I size M2? Let's say for a given M1 of W by L, how do I size M2? How do I set up this value of R2? Because ultimately, this value of R2 will set up this voltage, right? And if you assume this is VDD, right? So you cannot put any arbitrary value of R2, right? So there will be some constraints on the value of R2 which will set this voltage, the gate of M1. Which in turn will set up some constraints on which in turn will set up the voltage at the gate of M2, right? Which in turn will set the current on the M2 stack, and then you basically use the same current equations to figure out what are the limits of, I mean, is there a limit on R2 or is there a constraint on W by L of M2? Okay, but for all of these, you start off with assuming that both M1, M2 is in saturation, and you can also start assuming, okay, you can start assuming that M1 and M2 in saturation, and that would be a good starting point to figure out what will be the VGS. From there, you can figure out what is the minimum voltage required to keep M2 on, and so on, right? So, do it yourself. We can discuss it in the next class in more detail, right? Okay, any questions with whatever we have been talking about till now? No? Okay, we'll stop here because we'll have to distribute the sheets, right?